Welcome back, students. We'll be starting with the next algorithm, that is Warshalls algorithm. So here the input to this algorithm will be an digraph using which we will have to create a transitive closure. A digraph is a graph with directed edges. Now we have to write the adjacency matrix of this digraph, which will be acting as an input, and to this we need to find out the transitive closure. So we know how to represent the adjacency matrix. The adjacency matrix of a directed graph is the Boolean matrix that has 1 in its ith row and jth column if and only if there is a directed edge from vertex I to j, and otherwise it is 0. But transitive closure is T of ij of a directed graph with n vertices can be defined as a Boolean matrix in which the element in the ith row and jth column exists when there is a non-trivial directed path from ith row, ith vertex to the jth vertex. Let me take one sample graph for you and explain here. So you can see here I have taken vertex I and j. If there is a direct edge, then I am going to represent 1, if not 0 in adjacency matrix. If there is a directed edge from ith vertex to j. In case of transitive closure, I will be looking for a directed path from ith vertex to j. So if there is no direct edge between I and j, at least if there is a path from I to k and k to j, I will be searching for a directed path from I to j. If it is existing, then I will be representing it as 1, otherwise 0. Next. So here I have represented the same thing, and in order to traverse this, actually it will take more number of traversals. We can do it even with the DFS and BFS, but since the number of traversals will be more, we are adopting this Warshalls technique. Here, each time we will be considering the submatrix that is obtained as an input to the next matrix. So we will be starting with R0, that is the first adjacency matrix representation, using which we will be constructing R of 1, that is which contains the information about the path using 1 as the intermediate vertex. Next time this will be acting as an input, and I will be considering even vertex 2 as the intermediate. So 1 and 2 as intermediate. What are the possible paths that are available will be looked into. Next time R2 will be acting as an input to R3, which will consider 1, 2 and 3 vertices as the intermediate vertices. And finally, whatever is the graph representation up to n. So it will reflect whether the path exists between all the vertices in the digraph or not. So that was about the explanation. Next, moving on to one example. Let me take one example to first represent the adjacency matrix R0. You can see here I have taken, there is a path between 1 and 2. So I have represented it as 1. And there is no other path to vertex 3 and 4. So it is all 0. 1 to 1, no self loop. 1 to 3, 1 to 4, no direct edges. Similarly, from 2, there is a possibility to 4. Okay. And from 2, there is a possibility to 4. So you can see here, I have represented from 2, there is a possibility to 4. I have represented it as 1. The rest is all zeros. And 3, there is no directed edge towards all the other vertices, so it's all zeros. Next, moving on to 4. 4 has a direct edge to 3, and it also has a direct edge to 1. So you can see here it has an edge to 1 as well as it has an edge to 3. So I have represented it as 1. So if there is an edge, I will represent it as 1. If there is no edge, I will represent it as 0. Very simple. That is your adjacency matrix. Next, we will be moving on to R1. Using this as the input, I have to check whether taking 1 as an intermediate vertex, how far I can, whether there is a path. So I'll show you the reflections here. via 1 I have to move to other vertices. So all the vertices have to be considered. So you can see here 1, 2, 3, 4, all vertices I have written. Now starting with 1. Using 1 as an intermediate, can I move where? Already we have seen it in the adjacency. So I can go up to 2. That is okay. Next, vertex 2. Using vertex 2, using 1, can it reach any other vertex? No. So no changes. 3, there is no directed edge at all. So it's always 0, 0. Going on to 4. So you can notice here, using 4, vertex 4, using vertex 1 as an intermediate vertex, I can reach 2. So 4 can reach 2 via 1. So that is reflected here. 4 can reach 2 via vertex 1. So that is represented as 1. And 4 can reach 3. There is a direct edge which was already the input. No changes here. Now, taking vertex 2 as intermediate. Already 1 is intermediate. Now we will be considering one more vertex as intermediate, that is vertex 2 also. So you can see here from 1 I can reach 2, there is a direct edge. From 1 I can using 2 I can reach 4 also. From 1 to 2, 2 to 4. So you can see here 1 to 4 I have updated it. Earlier it was 0, now it is 1. Next, from 2 there is only possibility to go to 4, which is already shown here. 3, there is no possibility. Coming down to 4 once again. From 4 I can go to 1 and then to 2. Using 2 also I can move to 4. So you can see here from 4 I can move to 4. This is the updation. 4 to 1 already there is a direct edge. 4 to 2 via 1 I am going. 4 to 3 there is a direct edge. But 4 to 4 I am using via 1, 2, then I am able to reach 4. So that's the reflection. Similarly R3 I told you there is no edge at all. So we can't consider this. Moving on to R4. Now I can consider 1, 2, 3 and 4 also as intermediate in order to check whether there is a non-trivial path from one vertex to all the other vertices. So you can start with 1 and from 1 to 2 to 3, 1 to 2, 2 to 4, 4 to 3. There is a path. So now you can see 1 can reach 2 also, 1 can reach 4 also, 1 can reach 3 also. Using 4 as the intermediate. So you can see here I have reflected 1 to 1, 1 to 2 already it is there, 1 to 3 via 4 I can move. So that change is reflected. Next, taking vertex 2. From 2 I can reach 4, that is a direct edge. From 2 I can reach 3 via 4. So you can see via 4 I can reach 3. And from 2 I can reach 2 also. How? So you can see here 2 to 4, 4 to 1 and 1 to 2. So via 4 and 1 I can reach 2. So that is also reflected here. And so now you can see 2 to 1 I can reach, 2 to 2 I can reach and 2 to 3 I can reach using intermediate vertex as 4. So this is how the Warshalls algorithm works. Now this is explained in the form of an algorithm. So for initially I will be taking an adjacency matrix as an input and I am expecting a transitive closure as output. For that k is equal to 1 to n, I is equal to 1 to n and j is equal to 1 to n. Either when I am creating a Boolean matrix, either there should be a direct edge in between I and j, right? If I am finding k is 1, then I will be taking adjacency matrix as input here. So k minus 1, that is 1 minus 1, it will be 0. So either there should be a direct edge between I and j, or there should be an edge between I to k and k to j. Either of the two should be existing to update the value from 0 to 1. Since it is represented within 3 for loops, the time efficiency will be n3. I hope you have understood it. I'll give one more time regarding this. So if there is a direct edge between I and j, then we are going to represent it as 1. Otherwise, we will be finding whether there is a path available from I to j via k. K can be, first time it will be vertex 1 only, next time it will be 1 and 2 vertex, next time it will be 1, 2, 3 vertex, next time it will be 1, 2, 3 and 4, because our graph was representing 4 vertices. And here I will be taking every time 1, 2, 3, 4 vertices. All the 4 vertices I will be checking. Every time I will be checking from vertex 1 to all the other vertices 1, 2, 3, 4. Next time again I will be taking 2 and I will be checking it to all the vertices 1, 2, 3, 4. In that duration I will be taking k first time as 1 intermediate vertex, next time 1 and 2, next time 1, 2, 3 and next time it will be 1, 2, 3, 4. Thank you.